Right now, at this precise moment, an object from beyond our solar system is executing a maneuver we cannot observe. On October 21st, 2025, at precisely 1400 hours Universal Time, the interstellar visitor designated 3IATLAS reached solar conjunction, positioning itself directly behind the Sun as viewed from Earth. 8 days from that moment, on October 29th, it will achieve perihelion at 203 million kilometers from our star, traveling at 68 kilometers per second. During this critical window, when the object experiences maximum solar radiation, delivering over 33 gigawatts of power to its surface, every telescope on Earth is blind to its activity. The geometry is perfect. The timing is optimal. And according to the orbital mechanics that govern spacecraft trajectories throughout the solar system, this 8-day window represents the single most efficient opportunity for what engineers call an O-berth maneuver, a trajectory modification executed at peak velocity to maximize energy gain or loss. What makes this deeply unsettling is not that such a maneuver is happening. What keeps astronomers awake is that if it is happening, we have been locked out from witnessing it by design or by cosmic coincidence, and the distinction between those two possibilities grows harder to defend with each anomaly we catalogue. The Asteroid Terrestrial Impact Last Alert System discovered 3IATLAS on July 1st, 2025, from its station in Rio Hurtado, Chile. Think of Atlas as humanity's neighborhood watch, 4 robotic telescopes distributed across the globe, scanning the entire visible sky every 24 hours for objects that might threaten Earth. The designation 3I means this is only the third confirmed interstellar object we have detected entering our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The I stands for interstellar. The number 3 indicates sequence. Simple enough. What was not simple was what the follow-up observations revealed. Within 48 hours of discovery, telescopes from the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Observatory on Mauna Kea all turned their instruments toward the object. They found a marginal coma and a short tail 3 arcseconds in angular length. Cometary activity, except the object was already active at 6.4 astronomical units from the Sun, a distance where water ice remains frozen solid. NASA's Transiting Exoplanet Survey satellite had captured pre-discovery observations between May 7th and June 3rd, showing the object was bright and active even at that extreme distance. This indicated sublimation of volatile ices, more reactive than water, carbon dioxide, carbon monoxide, compounds that evaporate at temperatures where water remains inert. The James Webb Space Telescope confirmed this in early August, with NIRSPEC observations revealing a carbon dioxide-dominated coma with a carbon dioxide to water ice ratio of 8:1, among the highest ever recorded for any comet from any origin. That is our first data point. Active at impossible distances. Chemistry unlike anything in our solar system's inventory. Here is how to think about what we are observing. Imagine you are a detective examining a crime scene, except the scene is 400 million kilometers away and moving at 221,000 kilometers per hour. You cannot touch the evidence. You can only look at it through filters that break light into constituent wavelengths, revealing chemical fingerprints. What 3IATLAS is showing us is a fingerprint that does not match our database. Our comets, the ones born in the Oort cloud or Kuiper belt, have predictable ratios of volatiles because they formed under specific temperature and pressure conditions in our protoplanetary disk 4.6 billion years ago. 3IATLAS formed somewhere else, under different rules, in a stellar nursery with a different chemical inventory. The Hubble Space Telescope imaged the object on July 21st, revealing a teardrop-shaped cocoon of dust streaming from its nucleus. Subsequent observations on August 20th constrained the nucleus diameter to between 440 meters and 5.6 kilometers, probably closer to 5 kilometers based on the lack of detectable non-gravitational acceleration in its trajectory. That trajectory itself is hyperbolic, with an eccentricity of approximately 1.000016. In plain language, this object is not bound to our Sunday. It came from interstellar space. It will return to interstellar space. This is a flyby, not a capture. The SETI Institute's Allen Telescope Array began radio observations on the night of July 2nd, scanning for narrowband emissions between 0.9 and 9.3 gigahertz. Narrowband signals, those confined to extremely tight frequency ranges measured in hertz rather than megahertz, are considered potential indicators of artificial origin because natural astrophysical processes rarely produce such precisely constrained radio emissions except in masers, and even those are not stable over time. The Allen Array can detect signals drifting in frequency at rates consistent with transmitters on rotating planets or orbiting spacecraft, compensating for Doppler shifts induced by relative motion between transmitter and receiver. Dr. Wael Farah, chair of SETI and project scientist for the Allen Telescope Array, led the initial monitoring campaign targeting both narrowband continuous wave emissions and pulsed beacon-type signals. As of mid-October, no confirmed artificial signals have been detected from 3 IATLAS. That is important. It sets an upper limit. If the object carries a transmitter, broadcasting in the monitored bands with sufficient power, we would have seen it. We did not. That does not prove the object is natural. It proves that if it is artificial, it is either not transmitting in bands we did not monitor, or transmitting at power levels below our detection threshold at those distances. Let that sink in. Now we enter the territory where skepticism must fight against the accumulation of improbable details. The orbit of 3 IATLAS exhibits alignment within 5 degrees of the ecliptic plane, the disk containing all major planets in our solar system. For context, objects arriving from random interstellar directions should be distributed isotropically across the celestial sphere. The probability of an interstellar interloper naturally aligning this closely to the ecliptic plane is small. Not impossible, small. The object's trajectory brings it to close approach distances of 30 million kilometers from Mars on October 3rd, 97 million kilometers from Venus on November 3rd, 269 million kilometers from Earth on December 19th, and 54 million kilometers from Jupiter on March 16th, 2026. These are not random fly-throughs of empty space. The trajectory threads a path that samples multiple planetary environments in sequence. Again, not impossible for a natural object. The solar system is mostly empty, but the ecliptic plane is where the action is, where planets orbit, where gravitational perturbations are strongest. If you wanted to design a grand tour trajectory using gravity assists, you would aim for the ecliptic. If you are a comet ejected randomly from another star system, the odds of hitting that particular alignment are worth calculating. ESA's Mars Express and ExoMars Trace Gas Orbiter observed 3 IATLAS during its Mars approach between October 1st and 7th using the high-resolution stereo camera and color and stereo surface imaging system. The object's apparent magnitude from Mars was approximately 11, bright enough for orbital cameras to capture, though at 30 million kilometers separation, the resolution remained limited. Spectroscopic attempts using the NOMAD and OMEGA spectrometers aimed to detect molecular signatures in the coma, but signal levels were marginal. Images released by ESA on October 10th showed faint features around the object that are likely noise artifacts rather than secondary objects or fragmentation. No verified debris or separation events have been confirmed. The object appears structurally intact as it approaches perihelion. Observations from the Nordic Optical Telescope in the Canary Islands documented a remarkable evolution. During July and August, 3 IATLAS displayed what researchers initially described as an anti-tail, a plume of material extending toward the Sun rather than away from it. Radiation pressure from sunlight pushes dust and gas away from the Sun, forming the classic comet tail pointing opposite the direction of solar radiation. An anti-tail pointing sunward indicates anisotropic ejection, gas jetting preferentially from the sun-facing hemisphere due to uneven heating and volatile distribution across the nucleus surface. By September, this anti-tail had transitioned into a conventional tail pointing away from the Sun as the object's orientation relative to the Sun changed. The brightest emission shifted position over time, consistent with a rotating nucleus exposing different surface regions to solar heating. The mass loss rate from July through October is estimated at 2 million tons total, representing less than 0.00005 of the object's total estimated mass, exceeding 33 billion tons. We have observed only the outer skin layer, an average thickness of approximately 4 centimeters ablated from a 5-kilometer diameter body. The ratio is comparable to the palm of your hand relative to the length of Manhattan Island. We know nothing about the interior. We have seen only what the Sun has cooked off the surface. Here is the terrifying part. The object will remain unobservable from Earth-based telescopes from October 21st through early November as it transits behind the Sun, with angular separation less than 10 degrees, below typical coronagraph rejection angles, and overwhelmed by scattered sunlight. During this blackout window, 3 IATLAS reaches perihelion on October 29th. At closest approach, the solar radiation flux impinging on its surface delivers over 33 gigawatts of power, equivalent to at least 1/3 of the total power generated by 94 operating commercial nuclear reactors in the United States, the largest nuclear power producer in the world. That energy budget would be available for any number of processes, natural or otherwise. Sublimation of volatiles, certainly. Photochemical reactions in the coma, yes. Powering electronic systems if they exist, potentially. We will not know what happens during perihelion until the object emerges into observable sky in early November, and we can assess whether its trajectory, activity level, mass distribution, or any other measurable parameter has changed. The NOAA GOES-19 satellite, equipped with a CCOR-1 coronagraph, can observe objects close to the Sun from its geostationary orbit. Citizen scientist Worosheit Boonplod discovered 3 IATLAS in coronagraph images during late October, confirming the object's position even while ground-based telescopes are blocked by solar glare. However, coronagraph resolution and sensitivity are limited compared to dedicated deep space telescopes. We can confirm the object is there. We cannot resolve fine details or detect subtle changes in behavior. Post-perihelion observations will be conducted by ESA's Jupiter Icy Moons Explorer, known as JUICE, en route to the Jovian system. On November 4th, 2025, JUICE will pass within 64 million kilometers of 3 IATLAS, closer than any other spacecraft to the interstellar visitor. JUICE will attempt observations using its Janus camera, MAGIS imaging spectrometer, and particle sensors. Because JUICE is currently close to the Sun and using its high-gain antenna as a heat shield, data transmission rates are severely limited, and the spacecraft is positioned on the opposite side of the Sun from Earth, further constraining communication windows. ESA does not expect to receive data from JUICE's 3 IATLAS observations until February 2026. That is a 3-month delay between observation and data availability. If something significant occurs during JUICE's November flyby, we will not know about it until winter. NASA's Juno spacecraft, orbiting Jupiter, will have optimal geometry to observe 3 IATLAS in March 2026. when the object passes 54 million kilometers from Jupiter. Juno's suite of instruments includes ultraviolet, infrared, and radio sensors capable of characterizing the object's outgassing, thermal emission, and any electromagnetic activity at close range. Ground-based observatories will regain line of sight to 3 IAT-LAS around November 11th, when the object emerges in the eastern pre-dawn sky. Amateur telescopes with apertures of 3 to 4.5 inches using image stacking techniques have successfully detected the object at magnitude 15, demonstrating that citizen science networks can contribute valuable monitoring data. The object's brightness will peak as it moves closer to Earth through late November and December, though it will never become visible to the naked eye, remaining a telescopic target throughout its apparition. The critical observation window runs from November 11th through late December, during which astronomers will search for outburst activity, fragmentation, secondary objects, changes in coma, morphology, spectral signatures indicating new volatile species, or any deviation from the predicted gravity-only trajectory. Now, we must consider scenarios, not because we have evidence favouring one over another, but because the scientific method demands we construct testable hypotheses and identify observables that would distinguish between them. Scenario 1. Natural comet from an alien star system. This is the baseline, the null hypothesis. 3 IAT-LAS is a comet, a chunk of ice and rock, ejected from its home system by gravitational interaction with a giant planet or passing star, wandering interstellar space for millions or billions of years until it happened to intersect our solar system. The unusual carbon dioxide enrichment reflects formation conditions in a protoplanetary disk with different temperature gradients and chemical abundances than our own. The early activity at 6.4 astronomical units indicates high volatile content and low thermal inertia, consistent with pristine interstellar material never previously exposed to stellar heating. The ecliptic alignment is coincidental within statistical bounds, given the small sample size of 3 confirmed interstellar objects. The perihelion timing behind the Sun is orbital mechanics, nothing more. Observable predictions, continued outgassing consistent with solar heating models, possible fragmentation or splitting under thermal and tidal stress, gradual decline in activity as it recedes from the Sunday. Trajectory remains consistent with gravitational forces only, no non-gravitational acceleration beyond what can be explained by rocket effect from asymmetric outgassing. Scenario 2. Reconnaissance probe conducting passive survey. This hypothesis suggests 3 IAT-LAS is an artifact, a manufactured object designed to gather data on solar systems it transits without active signaling or intervention. The object would be dormant during interstellar cruise, activating instruments as it approaches stellar targets. The apparent cometary activity could be deliberate camouflage, outgassing, mimicking natural volatiles to avoid detection as artificial. Alternatively, the observed coma could be a legitimate ablation of a protective outer shell designed to shield internal systems during the high radiation perihelion pass. The ecliptic alignment and multi-planet trajectory would be intentional, maximizing scientific return by sampling diverse environments. The perihelion behind the Sun provides an opportunity for unobserved maneuvers or instrument calibration, using the Sun as a power source or gravitational anchor. Observable predictions, possible detection of narrowband radio emissions during or after perihelion, particularly if the object transitions from passive observation to data transmission phase, minor trajectory deviations unexplained by outgassing, indicating propulsive capability, deployment of secondary objects or probes during perihelion when observation is limited, anomalous thermal emission, inconsistent with passive solar heating alone, suggesting internal power generation. Scenario 3. Directed mission with specific targeting. This represents the most provocative hypothesis that 3 IATLAS was launched from another civilization with our solar system as the destination, potentially carrying instruments designed to study Earth specifically or to deploy assets within the inner solar system. The trajectory would be precisely calculated to optimize Earth approach distance and observation geometry. The perihelion timing, coinciding with solar conjunction from Earth's perspective, could be strategic, either to avoid premature detection during a critical deployment phase or to test whether Earth possesses observational assets positioned elsewhere in the solar system, capable of monitoring events behind the Sunday. The Oberth maneuver opportunity at perihelion would allow the main body to continue on its hyperbolic trajectory while releasing smaller probes with velocity kicks sufficient to place them on trajectories intercepting Earth or other targets within the solar system. Observable predictions. Emergence of secondary objects after perihelion with trajectories significantly different from 3 IATLAS's main path. Changes in the primary object's mass or brightness after perihelion, inconsistent with natural fragmentation. Trajectory modifications requiring delta-v budgets beyond what sublimation thrust can provide. Detection of electromagnetic emissions in SETI-relevant frequency bands, potentially including narrowband signals or modulated transmissions. The improbability stack grows heavier the more we examine it. Each anomaly individually can be explained. Early activity at extreme distance, high volatile content, unusual carbon dioxide ratio, exotic formation environment, ecliptic alignment, low probability event but within bounds, perihelion during solar conjunction, orbital mechanics plus observational selection effect, multi-planet approach trajectory, sampling artifact given small data set, anti-tail morphology, anisotropic outgassing from uneven surface heating. None of these singularly breaks the natural origin hypothesis, but when you stack them, when you multiply the individual probabilities, the cumulative likelihood that all of these features arise by chance in a single object becomes harder to defend without invoking either extraordinary formation conditions or considering that we might be observing something designed rather than randomly assembled. A research paper posted on RxIV in mid-October by a team from Harvard asks directly whether 3 IATLAS could be alien technology. The authors calculate power requirements for various propulsion and communication scenarios, estimate fuel budgets for Oberth maneuvers at perihelion, and discuss observational strategies to distinguish artificial from natural signatures. The paper ranks the object at level 4 on the Loeb scale, defined as unusual but not conclusive, a designation indicating the evidence warrants systematic follow-up despite the natural comet baseline remaining the most probable explanation. The paper explicitly avoids claiming the object is artificial while arguing that the possibility must be evaluated rigorously given the implications for humanity if confirmed. Other researchers have criticized this approach as premature speculation that risks sensationalizing an object with plausible natural explanations, potentially damaging public trust in scientific institutions if the extraordinary claims evaporate under scrutiny. The debate itself is revealing. Science advances through hypothesis testing and evidence accumulation, not through consensus or appeals to conservatism. If 3 IATLAS is natural, then careful observation and analysis will confirm that, adding to our understanding of cometary diversity and protoplanetary disk chemistry in other stellar systems. If it is not natural, then failing to investigate rigorously because the hypothesis seems improbable would be a catastrophic error, potentially missing first contact with non-human intelligence due to methodological timidity. The scientific community is divided not on whether to observe the object, everyone agrees that is essential, but on how much weight to assign to the anomalies and how publicly to discuss scenarios that venture beyond conventional astrophysics. Here is what we watch for in the coming months. November 11th through December 19th represents the primary Earth-based observation window, when 3 IAT LAS is visible in morning twilight before dawn. Observers will monitor for changes in brightness, coma morphology, dust production rates, and spectral signatures indicating new chemical species outgassing as the object moves away from the Sunday. Any sudden brightening or outburst activity would indicate either fragmentation events or internal structural changes. Spectrographic analysis will search for emission lines corresponding to exotic molecules not yet detected in the coma, potentially revealing deeper layers of the nucleus exposed by perihelion heating. Radar observations from Arecibo, if the facility is operational, or from Goldstone and Green Bank, could provide direct measurements of the nucleus size, shape, rotation rate, and surface roughness if the object comes within radar range during December. December 19th marks the closest approach to Earth at 269 million kilometers, still far outside any impact risk, but close enough for high-resolution imaging with Hubble and Webb. Hubble is scheduled to conduct ultraviolet spectroscopy observations in late November to determine sulfur-oxygen ratios and gas composition. Webb will observe in December post-perihelion using infrared instruments to detect water, carbon monoxide, carbon dioxide, carbonyl sulfide, ammonia, and other volatiles in the coma at unprecedented sensitivity. Any unexpected thermal emission, periodic variability, or spectral features inconsistent with natural cometry processes would elevate interest immediately. The trajectory itself remains under constant astrometric monitoring. Every observation refines the orbit solution, improving predictions of future position and constraining any non-gravitational forces acting on the object. Outgassing produces a rocket effect as sublimating gas jets preferentially from the sun-facing hemisphere, imparting small accelerations that perturb the orbit slightly from pure gravitational trajectory. These accelerations are measurable and predictable based on outgassing models. If the observed trajectory deviates from predictions in ways that cannot be explained by plausible outgassing distributions, that becomes significant. If secondary objects appear moving on different trajectories than the main body, that becomes critical. If radio emissions are detected, particularly narrowband signals with frequency drift characteristics indicating deliberate transmission rather than natural masers, that changes everything. March 16th, 2026. 3 IAT LAS passes Jupiter at 54 million kilometers. Juno will observe using its full instrument suite, including the Jovian Auroral Distributions Experiment for ultraviolet imaging, the Jovian Infrared Auroral Mapper for thermal emission, and the WAVES instrument for radio detection across a broad frequency range. Juno's position in Jovian orbit provides a unique vantage point, unavailable from Earth-based observatories. If 3 IAT LAS exhibits any behavior requiring revision of the natural comet hypothesis, Juno will be the asset most capable of characterizing it. After the Jupiter flyby, the object will exit the inner solar system on its hyperbolic trajectory, receding into interstellar space along a path that will not return it to our Sun's gravitational influence. Tracking will continue as long as the object remains within detection limits, potentially into 2027 if it remains sufficiently active or reflective. We are now in the waiting phase. The object is behind the Sunday perihelion has occurred, or is occurring, depending on when you are hearing this. We will not know what happened until the object emerges into observable sky in November. That is the nature of astronomy at these distances and speeds. We collect photons, we measure spectra, we calculate trajectories, and we wait for nature or something else to reveal its behavior. The question underlying all of this is fundamental. Are we alone? For most of human history, that question was philosophical, unanswerable by observation. Now we have instruments capable of detecting objects a few kilometers in diameter, moving at interstellar velocities, hundreds of millions of kilometers away. We have spectroscopes that can identify molecules in the gas clouds surrounding those objects. We have radio telescopes that can detect narrowband signals across vast distances if anyone is transmitting. We live in the first era where the question is not philosophical but empirical. We can look. We are looking. 3IATLAS is the third confirmed interstellar object we have detected. The next survey generation, including the Vera Rubin Observatory's legacy survey of space and time beginning full operations soon, will detect interstellar objects routinely, potentially multiple per year, once sensitivity thresholds improve. Each object is a sample from another stellar environment, a messenger carrying information about conditions light years away, a test case for how well we can distinguish natural from artificial at cosmic distances. If you want to stay on the timeline as this unfolds, as November observations begin and data from JUICE becomes available in February, as Juno conducts its March observations and the research community processes the accumulated evidence, subscribing ensures you will see the analysis as it develops. This is not a story that resolves in a single announcement. This is an observational campaign spanning months, data releases from multiple observatories on different schedules, papers posted to RxIve and submitted to peer review, debates at conferences and in journal letters. The picture will emerge incrementally. The value is in following the process, watching how science actually works when confronting anomalies that resist easy classification. Here is the final question. When you look at the stack of improbabilities, when you consider the ecliptic alignment, the unusual chemistry, the early activity, the multi-planet trajectory, the perihelion timing, the O-Birth opportunity window, and you weigh all of that against the baseline assumption that interstellar objects should be natural debris from other star systems, where does your assessment land? Are we observing pattern seeking, the human tendency to find meaning in coincidence, or are we observing contact, first evidence of technological artifacts from non-human civilization? Comment below with your assessment. Contact or pattern seeking? The data will decide eventually. Until then, we watch the sky and wait for November. The cosmos is under no obligation to make sense to us. It is under no obligation to be simple or to conform to our expectations. 3IATLAS is either an extraordinary comet demonstrating that interstellar formation environments produce chemical signatures radically different from our solar system's inventory, or it is something else, something designed, something sent. Both possibilities are profound. One expands our understanding of natural processes across stellar populations. The other expands the definition of what exists in the universe. November will bring data. December will bring more. By spring of 2026, we will have multiple spacecraft observations, spectroscopic analysis across ultraviolet, visible, infrared, and radio bands, trajectory refinement to centimeter level precision, and a body of evidence sufficient to constrain the hypothesis space. Right now, behind the sun, 3IATLAS is doing something. We cannot see it. We will see the results. That is how this works. We make predictions, we test them. We follow the evidence. If the evidence leads somewhere uncomfortable, somewhere that challenges assumptions about our place in the universe, we follow it there anyway. That is the method. That is the only method that works. The object emerged from interstellar darkness, traveling at speeds that prove it came from beyond our sun's gravitational binding. It will return to that darkness, accelerating outward on a hyperbolic path, carrying with it whatever information it collected during this brief transit through our system. We get one chance to observe it, one trajectory, one set of measurements, then it is gone. This is not a laboratory experiment we can repeat. This is nature, or something else, offering a single data point, and our job is to extract every bit of information that data point contains, before it recedes beyond detection limits and becomes another entry in the catalogue, another mystery added to the growing list of things we have seen but not yet understood. The universe is patient. It does not hurry. It does not explain. It simply is, and we are the ones asking questions, building instruments, developing methods, accumulating evidence, testing hypotheses, one object at a time, one observation at a time, until the pattern emerges or does not. 3IATLAS is part of that pattern. Whether it is a single unusual data point in a natural distribution or the first unambiguous detection of something intentional will be determined by the observations conducted over the next 6 months. We will know by spring. Until then, we wait, we watch, we measure, and we prepare for the possibility that the answer might be more interesting than the question.